When calculating the present value of arithmetic increasing or decreasing annuities in financial mathematics, these are the formulas that we typically use. And remember, an arithmetic annuity is an annuity where the payments increase or decrease by a set amount every period. Okay, and so when those payments are increasing, this is the notation and formula that we use. You have capital IA in parentheses, and then n bracket I, where n is the number of payments, and I is the effective interest rate that matches the frequency of the payment cycle. So if you have annual payments, then the interest rate should also be annual. And that notation is equal to this formula, where you have the present value of an annuity due, A double dot n bracket I, minus n times a present value factor to the power of n divided by I. But if your payments are decreasing for the arithmetic annuity, you use this notation and its corresponding formula. You have capital DA in parentheses, n bracket I, where n and I represent the same thing that they did for arithmetic increasing annuities. And that notation is equal to n minus the present value of an annuity immediate, an bracket I, divided by I. Okay, and so these formulas work. They will calculate the present value of an arithmetic increasing or decreasing annuity, but these are not always the most helpful, particularly from the perspective of efficiency, especially when you're looking to calculate these types of annuities in the BA2 Plus financial calculator. Okay, these formulas are simply just not very convenient when using this calculator. You have to split up these formulas into different calculations, do one piece at a time, and then put it all together, which is a time-consuming process. But there is a better way. There is a way to actually calculate arithmetic annuities, whether they're increasing or decreasing, pretty quickly in the BA2 Plus calculator. But there is some work that goes into it, because the BA2 Plus calculator doesn't have a specific function or feature that calculates arithmetic annuities. Instead, you have to learn a little trick. And that trick is the focus of this video. It's called the PQ method, and we're going to get to that in a little bit. But before I show you that method and how it works, I do want to show you the motivation behind it, why we want this method, where it comes from, and ultimately how it works. Okay, so if you just want to learn the method, feel free to use the chapters on this video to skip to that part of the video. But if you want some more context around it, then keep watching. Because as I've said, these two formulas are inconvenient for using with the BA2 Plus calculator. They are pretty inefficient. But not only that, these two formulas also have some specific requirements that have to be met when you set them up. And here's what I mean by that. For an arithmetic increasing annuity, when using this notation that represents this formula, whatever number you multiply by that notation or by that formula, the number you put out front, in this case I'm representing it with x, the value of x has to be the amount of the initial payment of the series of payments for that annuity, and it has to be the amount that each payment increases by. So for example, if we let x be 100, then that would mean that for this arithmetic annuity, the first payment or the initial payment is $100, and every payment increases by $100. That is what this notation would represent if you're multiplying it by 100. In the same way, for an arithmetic decreasing annuity, the number you multiply by that notation, in this case I'm representing it with y, the value of y has to be the amount of the final payment and the amount that each payment decreases by. So for example, if we let y equal 100, then what that would represent is an annuity where every payment decreases by $100, and the final payment of that series is an amount of $100. Okay, that is what that would represent. But if you've spent any amount of time calculating arithmetic annuities, then you know that not every arithmetic annuity is structured like that, right? Not every arithmetic increasing annuity has an initial payment that is the same amount as the increment of the payments. And not every arithmetic decreasing annuity has a final payment that is the same amount that every payment was decreasing by. That doesn't always happen. And so in a scenario where the initial payment for an arithmetic increasing annuity is different than the amount that each payment increases by, or in a scenario where the final payment for an arithmetic decreasing annuity is not the same as the amount that every payment decreases by, things get a little bit tricky. We can't just get by with these formulas alone. What we end up having to do is break up the series of payments into two series of payments. One of them will be a level annuity, and the other will be an arithmetic annuity. Okay, and I want to show you what this looks like so that you can see how much work goes into this and the amount of time that you're going to save with the PQ method, because this is something that you don't have to worry about if you calculate arithmetic annuities in your BA2 Plus calculator with this method that I am going to show you in just a bit. And so as a quick example here, Here I have a set of 5 payments from an arithmetic increasing annuity. The first payment is $150, and then every payment after that increases by $50, right? We go from 150 to 200 to 250 to 300 to 350. So there are 5 payments. The first is 150, and all of them increase by 50 each period. So you could not calculate the present value of these payments by writing 50 IA 5 bracket I, right? That would not work because 50 is not the amount of the initial payment. It's just the amount that every payment increases by. So what we would have to do here to calculate the present value of this arithmetic annuity using the traditional formulas and notation is split up this series of payments into 2 series of payments. And the way that I recommend that you would split up those payments is to first write out a series of payments where the increment is the first payment, right? So in this case, every payment is increasing by $50. So for the first stream of payments, you would make the first payment $50 and then just increase it by 50 every period. So we get 100, 150, 200, 250. All right, so that's one of the streams of payments, but then you get the other one by subtracting out these values from the original payments. Okay, that will give you the remaining amount in each payment for each period of time. And if you do this right, it should give you a series of level payments. Okay, 150 minus 50 leaves you with 100, 200 minus 100 is 100, 250 minus 150 is 100, 300 minus 200 is 100, and 350 minus 250 is 100. So at each period of time, we have a payment of $100. That is a level annuity. Okay, so these 2 streams of payments are equivalent to the original series of payments. They still add up to the same amount of the original payments. It's just that we're looking at it in a different way. So what we could do is calculate the present value of each of these series of payments individually. And so here's what the present value would look like. And by the way, this is an annuity immediate scenario. I want to value the present value at time 0, and the first payment is at the end of that first period. So we are working with an annuity immediate, not an annuity due. Okay, just to make that clear for when I set up these notations, but to calculate the present value, we could start with the level payments. We have 5 payments of $100. So for the present value of an annuity immediate, that would be 100 A5 bracket, and then the interest rate. I haven't given an interest rate here, so I'm not going to write it, but just know that there would be an interest rate there. But then we would add that to the present value of these payments valued at time 0, which do form an arithmetic increasing annuity. The first payment is $50, and every payment increases by $50. So you'd have 50 times IA5 bracket, and then the interest rate. And that's it. This right here would represent the present value of this original series of payments. We just broke it up into 2 pieces so that we can make use of our known formulas. Okay, and so just so we can compare this later, when we do use the PQ method, if I say that the interest rate here is 5% or 0.05 as a decimal, then the present value here, if you were to go through and calculate this using the formulas, you would get $1,061.27. All right, I rounded off to 2 decimal places there. There are more decimals, but I did round it off. Okay, I'm not going to show you the actual calculation here, as that is not the focus of this video, but if you were to use these 2 notations with an interest rate of 5%, this is the present value that you get for this series of payments. And so this method works. This is how you would go about calculating an arithmetic annuity like this using the formulas and notations that you know. And you could also do a very similar process for an arithmetic decreasing annuity where the final payment is not the same as the amount that each payment decreases by. You can calculate those annuities in this way. And this is the way that I mainly teach it in my other financial mathematics videos, particularly because those videos are focused on the concepts and not so much on using the calculator. But clearly this method is not efficient. This would be pretty slow if you're going to use the BA2 plus calculator. Sure, calculating the level annuity may go pretty quickly, but as I mentioned earlier, that is not the case for this notation or this formula. So we want a better way. We want a quicker, more efficient way to calculate arithmetic annuities in the BA2 plus calculator. And thankfully, that better way does exist. And so now I'm going to show you that method, specifically where it comes from first, and then I'll show you how to use it. And so to show you where it comes from, we have to generalize a scenario like this. Let's say that we have a series of payments where the initial payment is an amount P, and then every payment after that increases by an amount Q. All right, so the first payment is P, The second payment is P plus Q, and then the third payment is P plus 2Q because we would be adding another amount of Q to the previous payment. So P plus Q would be P plus 2Q. Okay, and so this would continue up until t equals n for the nth payment, where you have P plus n minus 1 times Q. And where that comes from is notice that the number in front of Q for each payment is 1 less than the value of time. All right, so it was 2Q for t equals 3, 2 is 1 less than 3, and for time 2, you just had P plus 1Q. 1 is 1 less than 2. That pattern will continue for all other periods of time. So that's why for t equals n minus 1, the payment is P plus n minus 2 times Q, because n minus 2 is 1 less than n minus 1. All right, same thing over here. N minus 1 is 1 less than n, and so that's where that comes from. Okay, so this is our general series of payments that form an arithmetic annuity, and that could be increasing or decreasing. If it's increasing, Q is positive, but if it's decreasing, then Q would be negative. You would be subtracting Q and subtracting 2Q and so on. But to keep things simple, for now we're just going to think of Q as being positive. But if we were to set up the notation for how we would calculate the present value of this series of payments, here's what that would look like. You'd have the present value is equal to all of these payments valued at time 0, but we could split them up into two series of payments just as we did in our example earlier. We'll have a series of level payments of P every period, and then another series of payments that are increasing by Q every period. So you have Q at time 2, and then that increases by Q every period until time n. Okay, so for the level payments P, the first payment is at time 1, and so we can use the notation for the present value of an annuity immediate to value those n payments of P at time 0. All right, so that would look like this. We would have P times a n bracket, and then I if you want to write in the interest rate, but to keep things simple, I'm not going to write it, just so the work looks a little bit neater. Okay, but then we would add that to the present value of the arithmetic increasing annuity, where you have a payment of Q at time 2, and then every payment increases by Q until time n. All right, but you have to be careful here, because the first payment is at time 2, there is not an n number of these payments, but rather n minus 1, right? If there are n payments of P, then there would have to be n minus 1 payments of Q because there are no Qs at time 1, right? Q starts at time 2, goes to time 3, all the way to time n. All right, so we would have Q times that notation, IA, and then n minus 1 bracket the interest rate. All right, there are n minus 1 payments for that arithmetic increasing annuity with an initial payment of Q, and every payment increases by Q. Okay, but now we're not done yet. There's actually one more adjustment we need to make, because this notation is an annuity immediate formula or notation, which means that this notation values the stream of payments one period before the initial payment. And if the initial payment of Q is at time 2, then this notation would value all those payments at time 1, one period before the first payment. But that's not where we want this present value to be valued. We want all of these payments valued at time 0. So if this notation currently values all the payments at time 1, we need to bring it back 1 year by multiplying by a present value factor, specifically to the power of 1. So we need to multiply that notation by v. Okay, so I hope that makes sense. This notation values all those payments involving Q at time 1, but multiplying it by v brings it back 1 period. Okay, and so this would calculate the present value of this series of payments. But we can simplify this. If we write out the formula for this notation, we can do some interesting simplifications. We're going to let the level payments alone. We'll still have P times a n bracket, but then we're adding that to Q times the formula for this notation, where the number of payments is n minus 1. So here's what that looks like. In the numerator, you'll have the present value of an annuity due, but remember that the number of periods is n minus 1, and then you subtract the number of payments, n minus 1, times a present value factor to the power of the number of payments. So we have n minus 1, and that's all divided by the interest rate I. Okay, and don't forget, you're multiplying that notation by v, so multiply by v. Okay, now in order to simplify this further, we will also have to write out this notation for the present value of an annuity due, So things are going to get a little bit messy for a second, but then there is going to be a lot of nice simplification that we can make. Okay, so rewriting this again, we have P times A n bracket plus Q multiplied by this formula, where I'm going to rewrite this notation. Remember that A double dot n bracket I is equal to 1 minus v to the power of n divided by 1 minus v. So we'll have the same thing here, but replace that n with n minus 1. So we have 1 minus v to the power of n minus 1 divided by 1 minus v, and then minus n minus 1 v to the power of n minus 1 divided by I. Okay, now where I want to go from here is multiply this v into the numerator of this expression. If we do that, we still have p times a n bracket plus q, but now I'm going to multiply this v into the numerator of this expression. So we have to multiply it by each part. So starting with this part, we're going to multiply v by it. So v would be multiplied into the numerator. You'll multiply v by 1 and by negative v to the power of n minus 1. All right, so here's what you'll get. You'll have v minus v to the power of n minus 1 times v. But since we're working with the same base of v here, when we're multiplying, you can add the exponents and have n minus 1 plus 1. So that 1 and negative 1 would cancel out, just leaving you with v to the power of n. And that's divided by 1 minus v. Okay, and the same thing is going to happen when you multiply this v by this term. V to the power of n minus 1 times v will just be v to the power of n. So we have minus n minus 1 times v to the power of n, and then we still have I in the denominator. All right, now this doesn't seem all that helpful right now, but it will eventually. We do have to manipulate this expression a little bit more. And don't worry if the following steps don't exactly make sense to you at first. We're going to do some interesting algebra things here, but don't worry about how would I know how to do that, because this is something that you don't have to know how to do. I'm just showing you the work or the derivation behind where this PQ method comes from. So don't get overwhelmed by the next couple steps. As long as you can follow the algebra, that's good enough. But to help us simplify this numerator into a form that is desirable, to help us find a quicker method for calculating these annuities in the BA2 Plus calculator, what I'm going to do is use a little nifty trick of adding a form of 0. And this is going to seem weird at first, but I'm going to add v to the power of n and subtract v to the power of n right here in the numerator. And you might think at first that that seems illegal, but it's not, because v to the power of n minus v to the power of n is 0. Okay, so even though we're adding terms to the numerator here, we're not really changing the value because these two terms combine to be 0. It's okay that we do that. You can add 0 to something and it doesn't change the value of that thing you're adding 0 to. Okay, so we can do this, and the reason we do that is we can combine this term and this term because they are like terms. Technically they're all like terms, but I'm just going to focus on these two because they're both negative. So you can add their coefficients nicely. You can add negative n minus 1 and negative 1, right? If I do that on the side here, we have negative n minus 1 plus negative 1. So you'd have negative n plus 1 minus 1. So 1 and negative 1 cancel out, just leaving you with a coefficient of negative n. So these two terms combine, and you'll just have minus n times v to the power of n. Okay, so the next step here, if I rewrite everything else again, we still have p times a n bracket plus q multiplied by that fraction. We have v minus v to the power of n divided by 1 minus v. And then I'm going to move this positive v to the power of n to be the next term. So we have plus v to the power of n. And now we can combine this term and this term. As I just showed over here, their coefficients combine. Negative n minus 1 plus negative 1 become negative n. So we have minus n times v to the power of n. Okay, and then the rest of this is not needed. We just have I in the denominator. Now what we want to do next is actually combine these two terms. And the way we can do that is by getting a common denominator between them. So this fraction has a denominator of 1 minus v. So to get this term to have a denominator of 1 minus v, we need to multiply it by a form of 1 minus v divided by itself. All right, so I'm actually going to do that right here in this step. I'm going to multiply v to the power of n by 1 minus v divided by 1 minus v, okay? And now I'm going to do some side work because I don't want to rewrite this over and over again. I want to show you what these two terms will simplify to if you combine them after getting that common denominator. All right, so a little bit of side work here. What we're working with are these two terms. So we have v minus v to the power of n divided by 1 minus v plus v to the power of n times 1 minus v divided by 1 minus v. Now these two terms have the same denominator, so we can add the numerators, and we also want to distribute v to the power of n through this quantity. So doing that, we get v minus v to the power of n plus v to the power of n minus v to the power of n plus 1. All right, these two terms come from here, and then v to the power of n times 1 is v to the power of n, and v to the power of n times v, you can add the exponents and get v to the power of n plus 1. And all of that is divided by 1 minus v. Now here's what's cool. Notice that we have a negative v to the power of n and positive v to the power of n. Those cancel out, and so you just have v minus v to the power of n plus 1 divided by 1 minus v, and these two terms have a common factor of v that you can pull out, and so I'll do that here. This would be equal to 1 minus v to the power of n divided by 1 minus v times v. Okay, this v is a v that I pulled out from the numerator. I pulled it out from this term and this term, so v becomes 1, and v to the power of n plus 1 just becomes v to the power of n. That plus 1 is gone. And this is what we have been working towards. This right here, 1 minus v to the power of n divided by 1 minus v, that's just the formula for the present value of an annuity due, right? It's that same exact formula that I wrote earlier. I'll write it again. We know that a double dot n bracket I is equal to 1 minus v to the power of n divided by 1 minus v. That is exactly what we have right here. So this is equal to a double dot n bracket I times v. And here's what's interesting about that. By definition, the present value of an annuity due multiplied by a present value factor is equal to the present value of an annuity immediate. Okay, remember, a double dot n bracket I is equal to a n bracket I times 1 plus I. So you take the present value of an annuity immediate and bring it forward one period, and you get the present value of an annuity due. And so if you were to solve for the present value of an annuity immediate, you would divide both sides by this accumulation factor, which is the same as multiplying the present value of the annuity due by a present value factor. So you get a double dot n bracket I times v equals a n bracket I. Okay, so that's exactly what we have right here. So the bottom line here is that these two terms right here that we've been working with in this side work all simplify to just a n bracket I. Or in this case, since we're simplifying our notation, it's just a n bracket. Okay, we can finish off our side work with that. That is all that is equal to, which is really nice. So replacing these two terms with that notation, here's what we get next for our present value equation. This is equal to P times a n bracket plus Q times a n bracket minus n v to the power of n divided by I. And that is a really nice formula. In fact, you might be familiar with this formula. This is known as the PQ formula, which is not the PQ method for the BA2 Plus calculator. This is something different. This is if you just want to use notation and formulas to calculate the present value of an arithmetic annuity where the initial payment is different than the amount that the payments increase by. All right, this is an alternative formula to the method I showed you earlier of splitting up the payments. This is an equivalent way to calculate the present value, but this is still not super convenient to put into our calculator. All right, so to get this in a form that we can use for the BA2 Plus calculator, we do need to do a little bit more simplification. What our goal is going to be is to combine the terms of this expression that involve this annuity immediate notation. So what I'm going to do is multiply Q into the numerator of this expression, and then split up the numerator and have two terms. We'll have Q times a n bracket divided by I minus Q times nv to the power of n divided by I. All right, so that looks like this. We'll have P and then a n bracket plus Q times a n bracket divided by I minus Q times n v to the power of n divided by I. Okay, and now I'm going to continue that work over here because we're almost there. We've almost found our PQ method. If we pull out the common factor of this annuity immediate notation from these two terms, we'll be left with a coefficient of P plus Q divided by I multiplied by A and bracket, right? We pulled this notation out of these two terms, so you're just left with P and Q divided by I. And then for this term, I'm just going to move the present value factor outside. So it'll look like this. We'll have minus Q times N divided by I times V to the power of N. And there we have it. This is what we have been working towards this entire time. Again, you don't need to know all of this work. I just simply showed it to you so that you can see where this formula comes from. Because what this is right here is our PQ method. This is an equation that you can work with in the BA2 plus calculator. This part right here, P plus Q divided by I, would be the amount of the payment for an annuity immediate that has an n number of payments and an interest rate I. And then this amount right here, minus Qn divided by I, we would think of that as the future value because that value is being brought back an n number of years. So that must mean that this amount, whatever it is valued at time n in the future, and it's being brought back to the present an n number of periods. All right, and so those are values that you could input for the TVM buttons on the BA2 Plus calculator. And I'll show you that in a second, but to further explain what's going on here, essentially what this method is doing is expressing an arithmetic annuity as a level annuity, or sometimes it's called a synthetic level annuity because really it's not a level annuity, but it's written in such a way that we can treat it like a level annuity. So you could call it a synthetic level annuity. What we're doing is overstating the real amount of the payments. P plus Q divided by I, this amount for the payments, is going to be more than what the payments would actually be for the annuity because we're making them constant rather than increasing by an amount, which is what they're actually doing. And because we're overstating the amount of the payments, we then subtract out the excess amount in the future. That's what this part is. We're subtracting out the excess amount, but valued at time 0. And that gives us the correct present value. Okay, so now let me actually show you how this method works. Let's use it on our example from earlier. Remember that this is the scenario that we were working with. The initial payment is $150, and every payment increased by $50. So the value of P is $150, and the value of Q is $50. And so what we can do is find the amount of the payment for this annuity and find the amount of this future value and put that into the BA2 plus calculator, okay? And then of course the value of N is 5 because we have 5 payments, and we'll just use an interest rate of 5% as I did earlier. So in your BA2 plus calculator, first of all, make sure that you clear out the TVM values before you do any new calculation. So to do that, hit second and then future value. That will clear out the TVM values. And then let's put in the easy information. We know that the number of payments is 5, so we'll hit 5 and then N. And we're going to use an interest rate of 5%, so we'll hit 5 and then I/Y. And now what we want to do is input the amount of the payment for the annuity, which is this expression right here, P plus Q divided by I, and then we'll input the value of the future value, which is negative Q times N divided by I. So let's do this calculation first. Let's do the payment. I'm going to start by taking Q divided by I, so I'll punch in 50 for Q. And then we're dividing by the interest rate, but be careful, don't divide it by 5 as in 5%. Divide it by the decimal equivalent, which would be 0.05. All right, let me write it down here. We are using an interest rate of 0.05, which is 5%, but we're going to divide 50 by 0.05. It equals, that's not the amount of the payment, that's just the Q divided by I part, but now add it to P, so we'll add 150, so hit plus 150, hit equals, and now that is the amount of the payment for TVM. So I'm going to hit the payment button. All right, so now that's done. All that's left to do is the future value. We're going to let the future value be negative Qn divided by I. So let's do 50 times N. That would be 50 times 5. So I'll punch in 50 times 5, hit equals, and then we'll divide it by the interest rate. So once again, you want to divide by 0.05, hit equals, but don't forget to make it negative. So hit the plus or minus sign, and now it's negative, okay? And so that's the future value. So you'll hit the future value button, and then you can calculate the present value. So hit the compute button, and then PV. And there it is. That's the same present value that I gave you earlier using the other method. We found that the present value is equal to $1,061.27 if you round to the second decimal place. Okay, now you will notice that the present value came out as negative in the calculator. That's fine. Just know that the actual present value is not negative, so you can ignore that negative sign. Okay, the present value here is positive 1061.27. Okay, so to summarize, this is the PQ method. For an arithmetic annuity with an interest rate I, an n number of payments, an initial payment P, and periodic increase or decrease Q, these are the inputs for the TVM buttons to calculate the present value of an arithmetic annuity. The payment is equal to P plus Q divided by I. The future value is equal to negative Q times N divided by I. N is equal to N. I slash Y is equal to I, but as a percentage, of course, and then you compute the present value. And this does work for both increasing and decreasing arithmetic annuities. The only difference between the increasing and decreasing case is that for increasing, Q is positive, and for decreasing, Q is negative. All right, so when Q is negative, the future value will be positive because the negative for Q will cancel out with this negative. So do keep that in mind. And most likely when Q is negative, the payment will end up being negative because you'll be adding a pretty big negative number to the value of P. All right, and that's okay. That will still get you the right answer when you compute the present value. And we'll end the video with a quick example of that. But one more side note, this does calculate the present value of an arithmetic annuity immediate. So if you want an annuity due, you just take that result, that PV, and multiply it by 1 plus I. It brings it forward one period, and now you have the present value of the annuity due version. And then if you need the future value instead of a present value, you still want to calculate the present value first, but then multiply that present value by 1 plus I to the power of n. All right, that will bring it to the future at time n. Okay, that is the PQ method. This is how you can efficiently calculate the present value of an arithmetic annuity using the BA2 Plus calculator. Okay, now as I mentioned earlier, before we close out this video, I do want to show you one more example, particularly where we have an arithmetic decreasing annuity. Hey there, before we move on to the next part of this video, if you are currently studying financial mathematics with the intent on taking the exam FM, then I want to give you a gift for watching this video today. I want to give you my free 6-week studying strategy guide for the exam FM. Inside the PDF file, I lay out a reasonable studying timeline that you can follow to prepare for the exam FM in just 6 weeks using my own content as well as some other resources online. By all means, it is not the only way to prepare for the exam, but it can certainly help you get started. So if you're struggling to stay organized in your studying of FM topics, or if you want an easy to follow schedule for preparing for your exam, then this guide is for you, and it's absolutely free. Just head on over to jkmathematics.com/studyfm 6 weeks. Once again, that's jkmathematics.com/studyfm 6 weeks, or you can find the link in the description. Okay, now back to the video. And so here's the example. In this case, we have 5 payments. The first payment is $500, and every payment decreases by 50. So we go from $500 to $450 to $400 to $350 to $300. All right, and for this example, we're going to use an interest rate of 0.05 again. So that will be the interest rate. Then N is the number of payments, and there's 5 of them. So N will be equal to 5. By the way, this is 5%, so you will input 5 into the calculator, but you do want to use 0.05 for these calculations. And so before we do these two, the payment and the future value, what are the values of P and Q for this example? Well, P is the initial payment, which is 500, so we have P equals 500, and Q is the amount that each payment increases or decreases by. In this case, they're decreasing by 50, so Q is negative 50. All right, they're not increasing by 50, so it's not positive. They're decreasing, so Q is negative 50. So calculating the payment here, we would have 500 plus, or really minus, right? Because Q is negative, so you'll have minus 50 divided by the interest rate 0.05. All right, so we'll put that into our calculator. And then for the future value, this is equal to negative Q which would make this 50 positive. So we'll have positive 50 times n, which is 5, divided by the interest rate, 0.05. All right, so this is the setup. This is what we want to put into the TVM buttons for our BA2 Plus calculator. So now let's do it. First of all, we want to clear out our work from earlier. So I'll clear the screen and then hit second future value to clear out the TVM values. And then let's put in our new information. We have a 5% interest rate, 5 payments, and then for the amount of the payment, we want to take negative 50 divided by 0.05 and then add 500. All right, so we'll put in 50, make it negative, divide by 0.05, hit equals, and then add 500. And that will be the amount of the payment. Notice that it's negative in this case. That's okay. So make that the payment. And now for the future value, you want to take 50 times 5 divided by 0.05, and that will be the right value. Okay, don't make it negative because that negative is gone. Since Q is negative, the future value will be positive in this case. Okay, the payment and the future value should always have opposite signs. So we'll take 50, multiply it by 5, hit equals, and then divide by the interest rate. So divide by 0.05. All right, and so that's the future value. Put that in, and then hit compute present value, and there it is. The present value of this arithmetic decreasing annuity is $1,752, and rounding to 2 decimal places, we have 89 cents. Okay, that is the answer to this example, if you want the present value of this series of payments. Okay, and as a comparison, using the other method, you would want to split up these payments. Splitting them up would look like this. You'd have a level series of payments of $250 at each period. So that would look like this. And then you'd have an arithmetic decreasing series of payments where the final payment is 50. So then adding 50 to go backwards, you have 100 here, 150 here, 200 here, and 250 there. All right, so the present value using notation and formulas would be 250 times AN bracket, or in this case, since there's 5 of them, 5 bracket, plus 50 times DA 5 bracket. Okay, and so using an interest rate of 5% or 0.05, you will get the same value that we got here. But obviously, the PQ method is a lot faster. You don't have to deal with these notations and the formulas that they represent. Okay, now that doesn't mean that you shouldn't know what those notations are. They can be helpful in other problems, but if you need to quickly calculate an arithmetic annuity, the PQ method is your friend. Okay, and so with that, that is it for this video. That is everything I wanted to talk about surrounding the PQ method. Hopefully you found this to be helpful. I didn't just want to give you the method and not explain anything surrounding it. So hope you found the motivation and the derivation behind it to be helpful, and it gives a little bit more context to what's going on when you do this calculation. But with that, if you do want to learn more about financial mathematics, feel free to check out the rest of my FM videos in my FM playlist that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.